We've laid out various laws of equivalence. We can use them to prove that specific pairs of formulas are equivalent to each other. Let's work through an example. Let's use the laws to show that P is equivalent to P and Q or P and not Q. I can either start with P and try to lay down a chain of equivalences that takes me all the way to P and Q or P and not Q, or I can start with that disjunction and try to lay out a chain of equivalences that gets me to P. Let's just try starting with P. We need to find something that our laws say P is equivalent to and write that down next, and then find something that our laws say that further formula is equivalent to, and so on until we get to P and Q or P and not Q. So what are our options here for the very first step? What do our laws say P is equivalent to? Well, let's look at De Morgan's laws. The first one says that if you have a conjunction that is being negated, that's equivalent to a certain disjunction. But P isn't a conjunction that's being negated. The first of De Morgan's laws also says that if you have a disjunction where both disjuncts are being negated, then that's equivalent to something else. But P also isn't a disjunction where both disjuncts are being negated. So the first one of De Morgan's laws is of no use to us here. It doesn't tell us anything about what further formula P is equivalent to. Likewise, the second of De Morgan's laws is also not relevant to us. P is neither the negation of a disjunction nor a conjunction where both conjuncts are being negated. Looking at the commutative laws, the associative laws, and the distributive laws, we can see that none of those can be applied to P either. What about the idempotent laws? Well, here we finally have a set of laws that tell us something about what further formulas P is equivalent to. The first law says every formula is equivalent to the conjunction of itself with itself. So from that first law, we can conclude that P is equivalent to P and P. The second law says that every formula is equivalent to the disjunction of itself with itself. So from that second law, we can conclude that P is equivalent to P or P. But while those are things that our laws tell us about P, we have to keep in mind our ultimate goal here, which is laying down a chain of equivalences that will take us from P all the way to P and Q or P and not Q. And it doesn't seem like either of those equivalences will help us with that goal. Likewise, the law of double negation also tells us something about what P is equivalent to. It says that P is equivalent to not P. So we could also make that our first step. But again, doesn't seem like that would help us make progress towards our ultimate goal. So let's keep looking. Consider the so-called domination laws. P is not the conjunction of a formula with absurdity, nor is it the absurdity symbol itself. So the first domination law says nothing about what P is equivalent to. Likewise, the second domination law also says nothing about what P is equivalent to. What about the negation laws? Well, P is not the absurdity symbol, nor is it the conjunction of a formula with its negation. So the first negation law is of no help to us. Likewise, with the second negation law, we can't apply that law to P either. Finally, what about the identity laws? Well, here we might be onto something. The first identity law says that any formula is equivalent to the conjunction of itself with the negation of absurdity. So it tells us that P is equivalent to P and not absurdity. And the second law says any formula is equivalent to the disjunction of itself with absurdity. So it says that P is equivalent to P or absurdity. Might either of those equivalences help us? Well, let's try building off of that first one. Do our laws tell us anything helpful about what P and not absurdity is equivalent to? Well, consider the second of the negation laws. It tells us something about what the negation of absurdity is equivalent to. It says that the negation of absurdity is equivalent to any formula of the form alpha or not alpha. In other words, take any formula you want, plug it in for alpha in the schema alpha or not alpha, and the second of the negation laws tells us that the resulting formula is equivalent to the negation of absurdity. So in particular, we could plug Q in for alpha in the schema alpha or not alpha. Right? That would give us the formula Q or not Q. And the second negation law tells us that that formula is equivalent to the negation of absurdity. So because of the law of substitution, that means that P and not absurdity is equivalent to P and Q or not Q. And now we seem to be getting closer to the formula that we ultimately want to arrive at, which is P and Q or P and not Q. In fact, we're just one step away. Take a look at the first of the distributive laws. It says, in effect, that conjunction distributes over disjunction. So if we have a conjunction where the second conjunct is itself a disjunction, which is what we have with the formula P and Q or not Q, we can take the first conjunct and conjoin it with each of the disjuncts that make up the second conjunct, and then put a disjunction sign in between the two resulting conjunctions. So with P and Q or not Q, we can conjoin P with Q and conjoin P with not Q, and then put a disjunction sign between those two conjunctions. And that gives us P and Q or P and not Q. So going through the whole proof in full, we start with P. Then the first of the identity laws tells us that P is equivalent to P and not absurdity. Next, the second of the negation laws tells us that not absurdity is equivalent to Q or not Q. So that law plus the law of substitution tells us that P and not absurdity is equivalent to P and Q or not Q. And finally, the first of the distributive laws tells us that P and Q or not Q is equivalent to P and Q or P and not Q. So there's a chain of equivalences taking us from P to P and Q or P and not Q, so those two formulas are equivalent.